Hello, this is my sixth lecture on graph theory. Today we will learn Prim's algorithm to find minimum spanning tree in a weighted graph, and also we learn augmenting path algorithm to find maximum matching in bipartite graph. So, first we talk about Prim's algorithm to find minimum spanning tree in a weighted and connected graph. So, Prim's algorithm it starts with a vertex which is the tree at the beginning, and then at every step it finds its nearest neighbor of the existing tree and include that nearest neighbor in the existing tree. First we talk about what is this nearest neighbor operation. So, here is the operation. The nearest neighbor operations takes as input a tree T having vertex set S and produces a minimum cost edge, say I j, in the cart S bar. Okay, so we do not know what is this minimum cost edge and what is this cart also. I will explain in detail. Let me just finish this part, that is C I j is the cost associated with the edge I j. C I j is the minimum of C A b, the cost of the edge A b, where A belongs to S and B belongs to S complement. Okay. So, note that S complement is V minus S. Okay. So, let me give one example to illustrate this definition. I take this graph . So, these are the vertices of this graph, and A and C are adjacent, A and B are adjacent, B and E are adjacent, C D adjacent, D E adjacent, C B adjacent, and C E are also adjacent. And this is a weighted graph. weighted and connected graph. So, the weight of this edge AC is 0, this is weight 1, 2, 3, 2, 4, 2. Okay. So, now I will explain what is this minimum cost edge in the cart x y. Let me x bar. Let me take S is equal to say A and C, okay, and so S complement is equal to B, D and E. Now, what you do is that you what is the minimum cost edge in the cart. So, the minimum cost edge in the cart S complement is obtained in this way. So, this may be this is S consists of A and C. So, this is one part and S complement consists of B, D and E. So, this is another part. So, you are dividing the set of vertices into two parts basically S and S complement. Now, the cut S complement means cut S complement consists of these edges, the edge AB, BC, CE and CD. So, you see the weight of each of these edges and take the minimum. So, the minimum cost edge connecting in this cart S complement is basically A B. Okay. So, similarly, if you take say another S equal to say for example CB, this is first example, the second example. Then my S complement is equal to A, D and E, right. So, I can now CB is one part. Let me see. So, now CB is one part and A, D and E, this is another part, this is S complement. So, the edges, the cut consists of these edges, the cut consists of this edge, this edge, this edge, this edge and this edge. So, here the minimum cost edge in the cart, let me call it say S1 complement, in the cart S1 complement is now AB basically. So, this is again A B. Okay. Well, so now we know what you mean by the minimum cost edge in the cart is complement. Now, so we will write in this way: the nearest neighbor, for this example, A B is the output of the function or the operation nearest neighbor of S complement. Or the other way of writing this S complement is you just write the set of vertices in the tree T is that is the set of vertices of tree T is S. Okay. Next, we talk about the Prim's algorithm. So, the input to this algorithm is a connected graph. If it is not connected, you will get a minimum spanning forest, not minimum spanning tree, and a vertex, any arbitrary vertex, say I naught, and the output is a minimum spanning tree. T. Okay, as I said that this algorithm start with a singleton tree. I mean the tree consists of one vertex. So, the T is initially this is the minimum spanning tree. Initially the T is the tree consists of vertex I naught, and this T is basically the set of tree edges. So, if the graph G is having n vertices, then tree will have n minus 1 edges, because we know that a tree with n vertices has n minus 1 edges. So, that is why we have this while loop, while this cardinality of tree, that is T is the set of tree edges, when this is less than n minus 1, you do the following. What you do is that you find out the nearest neighbor of T, the current T tree, the nearest neighbor of the current tree T. So, see before I wrote here S complement. So, here I wrote T, the only difference is that I mean once you know T, you know S complement, because S is the set of vertices of the tree T. Okay. And then you update your tree. So, T union I j. I will explain this algorithm of course, and when you are outside, when you have n minus 1 edges in your tree, you are sort of done, you got the minimum spanning tree, and you return, you are outside of this while loop and you return return t. Okay, so now I will explain this algorithm using an example, the same example. A C, B, D, E and F. So, these are the vertices. Again A C are adjacent, A B are adjacent, C B are adjacent, C D adjacent, B E adjacent, D E adjacent, E F and D F, they are adjacent, and also C and E are adjacent. Now, I write down their weights 0, 2, 5, 5, 4, 3, 4, 2, 1. Okay. So, let now I illustrate this algorithm using this example. Let I naught. So, the input to this algorithm gives a tree, gives a graph, weighted graph, and the vertex I naught. Let that I naught be equal to A, the vertex A. Okay, so now at this moment your tree consists of only one vertex, that is the vertex A. That is all. This is your tree. And what you have to do is that you have to find the nearest neighbor of. So, the S at this moment is equal to A. It consists of only one vertex, that is A, and you find the nearest neighbor of S complement. So, the nearest neighbor of this T. At this moment the T is consists of only one vertex A. So, that is equal to so this is S and its nearest neighbor is C. So, the output to this thing, to this operation is AC. Okay. So, another way of illustrating this one is that you make a small table like this one. So, this part is so this part is A, that means the set S, and this is S complement. So, S complement consists of B, C, D, E and F, and you can see that A and B there is an edge and weight is 0, A and C there is an edge and the weight is 0, A is not adjacent to D, E, F. So, you can keep this blank. So, this is the smallest one. So, the nearest neighbor is A C. This is another way of sort of computing the nearest neighbor. You can see from the figure also. So, this is at the first iteration, and at the second iteration you have now your tree is consist of one edge A C. So, your S is consists of two vertices A and C, and T consists of one edge, that is AC. So, again you find the nearest neighbor of T. So, one way of finding that is that A and C in one part and the remaining vertices are in the other part. That can be also represented in this way in the form of a table. So, AC and this is the elements in S, and in S complement you have B, D, E and F. You can check that A and B are adjacent and that is weight 1, D, E, F are not adjacent to A, C is adjacent to B and the weight is 2, similarly here it is 2 and 3. So, the minimum one is this one. So, AB is the output of the nearest neighbor operation at this stage, nearest neighbor of the current tree. Okay. So, now your T, you update T, then you update your T. T consists of two edges now, one is AC and the other one is AB, right, and then S consists of three vertices now, A, B and C, A, B and C, right. So, at the third iteration, what you do is that again you construct this table, A, B, C are the vertices in S, and in S complement you have the vertices D, E and F. A is not adjacent to B, E and F, B is adjacent to E, B is adjacent to E and the weight is 4. Similarly, C is adjacent to D and the weight is 2, and C is adjacent to E and the weight is 3, and the minimum one is this one. So, the output of nearest neighbor here C is CD, right. CD is the output of nearest neighbor operation with the current tree T. Well, so one more iteration. So, now you update your T. So, T is consist of the tree T consists of three edges now, that one is AC, AB and CD, and of course, your S is then S is A, B, C, D, right, A, B, C, D. So, at the fourth iteration what you do is that you make the table again A, B, C, D. So, A, B, C, D is in one part, and S complement is this. So, if you write it in the form of table, then what you get is that you have E and F in the other side, and you can see that the minimum one is CE definitely. This is the minimum one here. So, in the form of table it is 4 here, it is 3 here and it is 5 here. So, the minimum one is 3, and CE is the output of the nearest neighbor. of the current tree T, and so you update your T. Your current tree is consist of 4 edges AC, AB, CD and CE. Okay. So, since there are 6 edges, we need 6 vertices, one more edges is required, and that is the last iteration. The table for this one is that, so now S consists of everything like A, B, C, D and E, and S complement is F. So, we construct this table again. So, this side you have A, B, C, D, E, and you can check that this quantity is 5 and this is 5. You can pick any one of them. So, the output of the nearest neighbor is DF, which is the nearest neighbor of this tree. So, you update your T finally, and this is the final T. This consists of AC, AB, CD, CE and DF. Okay. So, we can also okay. So, we can show that tree edges here. So, the tree edges are AC, AB, CD, CE and BF, and that is the minimum spanning tree. Okay. So, we have learned how to find a minimum spanning tree using Prim's algorithm. It starts with one vertex, and at the first step it will find the nearest neighbor of that initial vertex, and once you get the nearest neighbor, now your tree is consist of 2 vertices, and again you expand that tree at every step until all the vertices are included or there are n minus 1 edges. Now, we talk about one one result, which is sort of explain why this Prim's algorithm is giving the correct answer. Let S be a subset of the vertex V, and of course, the S complement is V minus S. Let E be the minimum cost edge connecting S and S complement. Then this result says that E is part of MST. Okay. Well, so S is any subset of the vertex set V, and S complement is another part. and E is the minimum cost edge connecting S and S complement, then E must be part of MST. So, this lemma sort of gives a proof that the Prim's algorithm is correct. So, we will look at the proof of this lemma in the second part of this lecture. Thank you very much.